Hello everyone, my name is Eva Shake. Today I will be presenting on learning from imbalanced visual data. This is the topic for my research project. I will be discussing the dataset, my experimental setup, the method I tested, some early result, and what I planted to do next. So let's start with a brief introduction on what is the imbalanced data. In machine learning, imbalanced data is the classes in the dataset which are not represented equally. Some classes or categories have more sample than other. Here, the predominant label is an imbalanced dataset is called majority classes, and the less common label is called the minority classes. Imbalanced dataset is extremely common in the real world, like in fraud detection. The majority of the transactions are normal with only a few fraction of being fraudulent, and in medical diagnosis as well, there are fewer images of rare diseases than the healthy scan. So when we train our module using such data, the module trains on majority of the classes and tends to neglect the rare or minority classes, which result in unfair and biased machine learning module. So to handle imbalanced data, um, it is essential for creating fair and effective machine learning module. So for this project, I have used CIFAR10 dataset. It is very widely used and very well known for training image classification module. It has about 60,000 images of class of size 32 by 32 pixel, which is divided evenly into 10 classes such as airplane, automobile, bird, cats, and so on. The official C14 dataset is a balanced and is split into two parts, training and testing, where 50,000 images for training and 10,000 for testing. For my experiment, I have modified the training dataset to create my different imbalanced dataset for C410. The test set is untouched and balanced. The first imbalance is the long tail class imbalance, where each classes have fewer examples than the last one, creating a gradual drop off. Like in real world, where some animals are more common than the others. The second one is the step shift imbalance, where the half class have full example and the other half have very few. It replicates the scenario like disease detection, where some conditions are rare. And the third one is the almost single class imbalance. In this imbalance, one class is extremely common and the rest are rare, just like the fraud detection, where the fraud can be tiny fraction of all the transaction. So by comparing the method across all these three imbalanced datasets, my goal is to test the different techniques to handle imbalance and check if they are robust across the different imbalance ratio or not, and also check the strength and weakness of each approach in different imbalance ratio. So for the baseline of my experiment, I have used a popular deep learning architecture called DenseNet. It is a modern convolutionary network that is designed for future reuse. Each layer receives input from all the previous layer, which helps the module to learn more features. So first, I trained the DenseNet directly on each of the three imbalance ratio of CIFAR10 that I have created without using any special techniques. So here we can see the training and validation curve for my baseline DenseNet on the long tail dataset. On the left, you can see that the loss epochs of both the training set and the validation set. Both loss decrease steadily, indicating that the module is learning from the data. On the right, we can see that the accuracy curve for both training and the validation accuracy reached 80% by the end of the training, which seems good, but it is important to note that this overall accuracy is mainly driven by the majority classes. Because of the imbalance, the module learns to classify the common class well, but tends to misclassify the rare one. We can confirm by looking at the pre-class performance in the classification report. Here we can see how well the module performs for each classes as well as overall performance metrics. In Imbalanced, the module achieved an overall accuracy of 50%. Some classes like airplane and automobile have higher recall and F1 score, but classes like cat and truck have much lower F1 score. In SS imbalance, the accuracy improved to 74% and precision, recall, and F1 score are generally higher across most classes. In AS imbalance, the performance dropped significantly and the accuracy is just 59, and the F1 score are lower for most classes. As we can see, in AS imbalance, the CAT F1 score dropped to 0.24 compared to 0.59 in SS imbalance and 0.54 in L imbalance, showing the extreme effect of heavy imbalance. This highlights why it is important to use specific techniques to address the imbalanced data. So, to improve the result, I have tried two common techniques. The first is weighted random sampling. This is the technique of resampling the data during the training so the module sees majority class more often. And the second one is oversampling. Here I duplicate the data from the rare class so that each batches is more balanced. These both are the data level solution. They do not change the module itself but try to rebalance the input during the training. So after applying the weight random sample technique and oversample technique to handle the classes imbalance, I expect to see some significant improvement in the module performance, especially for minority classes. However, based on my result, I found that the overall improvement compared to baseline was quite modest. The accuracy and some metrics like recall improved slightly, but the module still struggle with certain classes, and also using oversampling can sometimes increase the risk of overfitting, since the module may see repeated example from the minority classes too often. So for my future work, I planned to use more advanced methods such as data augmentation and generative module to further boost the performance and prevent overfitting to make the training more robust and generalized, especially for the rare classes. Thank you.